Okay, so, right. So lots of things about random networks. We're going to talk about this for quite a while until you tell me to stop, probably. But I mean over the course of weeks. Okay, so it could get rather painful. Is this okay? Can you see this thing? Let me make sure this is... I mean, it's not... I don't think I can improve it. Let's see.
Oh, it's most of the size.
So I'll make that bigger. Okay, so I wanted to tell you that I've added... You'll be excited to know. So I've added some more slide sets, figuring out which ones I had. So there's random networks, which we're going through. We get to generating functions and networks. Deliciousness. This I have to improve. The applications around... I mean, it's there, but we might talk about that. I might leave it for a while. And then contagion. So this is all connected. Generating functions will help us here in certain ways. In certain ways we can do things kind of simply, actually. So we'll come back to that later on when we talk about mixed random networks. So these are networks where you specify all sorts of properties, right? There might be some big modular structure to it, and then everything else is random, right? So there are 30 characters here, 70 here, 40 here. There's some number of links between them, but everything else is random, right? It's randomized. There's that kind of thing. It turns out it's incredibly hard to, say, build a simple network that has a degree distribution and a particular clustering, right? There are certain, like you build out from random networks and you add structure to it. And you want to do this in a kind of a principled way. Like, for instance, that's really hard, right? That was a real struggle for people to figure out how to do that well. But at that point, maybe you're getting too far away from reality. You start a long way away from reality already. So, so there are certain kinds, because you can just march away from the simplest models into all the adjacent possible is enormous, right? There are all sorts of things we could do. And there's a gap between that and then real networks. So we'll go in certain directions which are profitable, but certainly not every one of them. All right, so there's more data sets there, and otherwise things are kind of so the last one's up there, amazingly. The first 10 minutes include this is ridiculous. They include because it all broke, right? So they include videos of struggling while I'm trying to figure out how to do it. Okay, so that's just amusing myself, I realize. Okay, so good. We are going to talk about a little more about random networks. Then we'll get into generating functions, which are, think about these guys. Yeah. We'll see how far we get. 2 lectures. All right. Right. Okay, so we got to this end statement, this end piece here, which was this oddness of the Poisson distribution. So Poisson distribution appears in many circumstances. It appears, in particular, for random networks. Right? Reach into this box. We pull out a thing. It will have, it's big enough networks, big enough M. Will always have a Poisson degree distribution. All right. And so here's a little thing. I threw this into assignment 5, so you guys can work on this, right? It's a small piece, but it'll be nice because we'll come back to it with generating functions and some other things. Okay, so you do this with sums, just by hand. Not a super hard thing. It's just being neat and tidy, and then we'll see. We'll get these things from generating functions as well. So it'll be nice. But this is a very important feature of the Poisson distribution. Is that the second moment to start with is the first. It's the mean squared plus the mean. It's the first moment squared plus the first moment, right? The first moment is the mean. So this is just its feature. So if we go to the standard deviation, which is the second moment minus the square of the first, the square of the median. The mean, sorry. Then, okay, so everything is here. This is the second moment. It's the square here plus this guy minus the square, so all of this cancels. So we have this odd circumstance that the variance, or the standard deviation squared, the variance is the same as the mean. If you think about what that means for the Poisson distribution. So if you have a Poisson distribution with a very high mean, well, you might have guys like this, and then go out further and further, you have a very high mean. Then the width of this thing, so here's the mean, say, roughly. Then the typical width of this thing, sigma, right, is equal to, 2 times the square root of the mean. So the width of this thing gets smaller and smaller relative to the mean. So if you look at it from a distance, the more you move away from 0, which means bigger and bigger networks with a higher and higher average degrees, then you start to see this really kind of, it's more like a delta spike. obviously not literally, but it's becoming narrower and narrower. But for low mean, it's always nice and sort of spread out. Okay, just a feature of that thing, but it is shrinking. All right, so this is a very, very special property. This is just a very special property, and there's a certain way that we make a big mistake when we think about how things spread, contagion, and so on. All right, these are really, really nutritious calculations. Really good fun. All right, not fun. Okay. All right, configuration models. So we've talked a little bit about how to build these things. So there's a sort of the theoretical one, which you can do, certainly, with simulations. You can say, okay, I've got n nodes, and then I'm going to test every link. With probably p, it'll be in, probably 1 minus p, it's out. That builds you a random network. Or you could throw m edges down. Totally exciting, right? Think about how to do that. So configuration model is our first step away from pure random networks. It's the crucial step away, right? This is the simplest or the most important thing that we add that's non-random. All right, so Poisson feels like it's a structured thing, but it's not. It's a result of randomness. That is an artifact of randomness. Okay. All right, so we're going to now say we're going to force a particular degree distribution. Anything we want, right? So it could be that everyone has degree 7. So that's right? So that would be pk equals delta k7, right? The Kronecker delta. So this is 1 when k is 7, 0 otherwise. It's a nice little, whoop, right? That's 7. We're dealing with discrete things, of course, so our distributions are defined on 0, 1, 2, 3, 4. Anything you want, any kind of distribution you want, right? So it could be one that's real, that's observed from a real network. So that's useful. You say, okay, I've got a real network, it's got this distribution. Now I'm going to make a random one that has that same distribution. Right, so how do you do that? We know how to build these pure random ones, but we need another way to build something where we say from the outset, we want this degree distribution. Right, so we're trying to find random sets that are in little corners of these boxes, right? Or tiny little spaces. The ones you don't get when you rummage around happily. Okay, so we can call these general or generalized random networks. Maybe I'll say generalized, I think. And you'll also see configuration model is another term that's just been around for a while. So that's, people will just say that. They mean this. Okay, so we're going to take, you can use the construction method that you have for the Erdős random networks where, right, there's a probably P of any two nodes connecting. And then you can do it like this. So you give, this feels, it's not, people will say this is generative, but you have to be careful with that, right? This is a way of making a kind of network, but it's not a real mechanism. This is an artificial way of constructing things, right? So people will use these words in different ways, just like the word model is used in very different ways across fields. Who knows what people are talking about? From a physics point of view, you want mechanisms that really are in the real world. You want to model them, right? You want to use those. You want to maybe guess or at least try to copy those mechanisms and use them in your theory to produce some output. All right. So this is, as I said, not a real mechanism. It's just a kind of a fun way to play around with it, and it gives you maybe some hooks into it analytically, although we won't really use it. So every node could have a weight, and then the probability of linking between any pair of nodes will be proportional to the product of their weights, right? And so you have to normalize this such that you get. So you say I want to have a particular average degree. And then you will figure out how many. So you sum up all of these products, right? So there's I guess this is what you want. There'll be a normalization. So the actual connection between I and J would be equal to the product of these two weights, and then you'd normalize. Let's call it I prime and J prime. You'd sum up by all of those. There's one way to do it. J prime, right? So this is the sum of all these products, and then multiply the whole thing by the average degree that you want. I think I got that right. Yeah. Okay. Yeah. Okay, that's fine. Fine. All right. So that kind of.
All the weights for I and all the weights for J.
Yeah, that's a double sum.
Okay.
Yeah. All right. So I could make it really quick. yeah. Yeah, so these are all the possible things. Then this is the particular pair. And so if we go back to Edish-Rennie, the weights are all 1. Everyone has a weight 1. Right. So it should make sense. So on the bottom, we really just have a sum of 1 over all the pairs. So we have n choose 2 on the bottom. So you could figure out that that gives us what we had before. That should just, so everyone, so the connection is the same. All right, so let's just fill that in a little bit, but we're going to try, I'll talk about this. I could, I have code for doing this. I should give you this code. All right. Yeah. It's nice code. A little bit of C code. Interfaced into MATLAB. But you can break it off and do whatever you want. But it's mex, so you can, it's actually structured so it's a mex file. Which is a torturous activity, yeah. But, really nice. You're in MATLAB, you write your little simple thing, which is good for MATLAB world, create matrices, and then go and use a real thing, which is written in C, to do the hard work. Right, so if you ever have a couple of for loops in MATLAB, it's time to stop. You should not be doing that anymore. It's good for a lot of things. I mean, it's built, Matrix Laboratory is built to add things in clever ways and mess around and make products and so on. But if you start to put little for loops all over the place, it can get very slow. All right. Maybe I'm talking about 1998. No, but it is true. C will just rampage through things. Okay, so we want to do this. We want to randomly wire up things. And this fits a little bit with... It feels a little more intuitive too. So this is going to be a better way. Say we get a real network which has a specific degree distribution, right? There's node 1, and it's got 5 links, and node 2 has 3, right? You actually have a real layout of nodes. What we want to do is then jumble that thing. So that seems like a reasonable procedure. All right? So we want to jumble it up and see how different the jumbled up versions are to the original one. We've talked about this a little quickly in POX. And of course, in general, and this was a big thing in POX, we have all the extra expansion pack stuff going on there with scale-free networks. You want to see how you actually get to these networks. This is not really a mechanism, what I've been saying. All right. Okay, so this is, we're going to move out to, you've seen these with scale-free networks, so-called scale-free networks, but networks that have parallel distributions for the degree. These are building them in a very different way, right? So we're going to actually say, we're going to allocate the degrees to nodes and then connect them up. All right, so 1,000 nodes, just to give you another picture of these things. The decay is going to be minus gamma, exactly, right? So there are no isolated ones. Just none of them, because this also wouldn't make sense for that. And then we'll vary the exponent across a small range. So this is a range that you will know is, if the POX people will know, this is your mean is finite, your variance is infinite, right? Or if it's a finite thing anyway, then the variance is governed by the highest cutoff, the upper cutoff. So these are statistics of surprise situations. And we'll do this thing we did for pure random networks, right? So wiring is random apart from the degree distribution. So quite different. So the thing that's being varied across here is this exponent, right? There's when we had pure random networks, we dialed the average degree. We had a different way of scoping through the space. Here we're going from more extreme ones, right? These are ones where the tail of the distribution is broader. And as we move across these guys, we get to 2.91, so the tail is coming down, so the variance is, becoming smaller and smaller, relatively. Again, just one example, but you see this kind of, it's not a hairball actually. There are nodes with there are nodes with massive numbers of connections in here. You can kind of look at these a little bit and see that there's a hub structure to them, right? These well-connected ones. But that sort of goes away a little bit, and even here, this one didn't really get a nice giant component. But you can see that clear tree-like structure in the middle. These are just the largest components. right? So this one didn't take off properly, but you see that ring structure, right? There are ones in the middle that are hugely connected and then going out and going out. You know, a very common kind of structure in the real world. Just looking at them. Okay, good. Okay. So that's a configuration. We'll come back to that. But now this sort of allows us to think. Now we start to think about. All right, we can make them, but we can do a lot of theory with these things as well. Okay? We don't have to, build networks. We can think about them. So there are a couple of really important pieces here, right? So there's a degree distribution. But then there are. So that's okay. So that's about. Right. So that's key to how we think about networks, how we describe them. Again, something that was only really, really made clear to ourselves in 99 really. And so this is, okay, we've got a network, we're going to choose a node, we're going to point to a node at random, right? The n nodes, you roll your n-sided thing, and it comes up with 17, and you go to that one, and you look at its degree. So this is a probability that a node of randomly chosen has a certain degree. So really important for thinking about how these things are connected, how things spread on them, and not just random networks, but all sorts of networks is what happens if you jump on an edge first, right? So you're just going to leap out and jump on you're going to randomly choose from edges now, right? In graph theory, there's a lot of work on the sort of dual graphs and so on where you think about flipping between edges and vertices, but we'll do that a little bit. It's very important to think about. It actually becomes much more profitable to think about edges, to think about how things spread and so on. You really want to look at edges. Okay, so this is a start on, nodes are very natural. We're nodes, right? But actually you kind of want to live in edge space. You want to, theoretically. And we'll see some really nice stuff for diffusion later on. So diffusion is about how things spread out. It turns out, evenly things diffuse, they flatten out in spaces. A very beautiful thing happens for networks, which is really all about edges. Okay, so we have a P, so we'll go to Q. So Q sub K is the, have to think about it. So we're going to randomly choose an edge, and then we're going to flip a coin, and we're going to randomly go to one end, and then look at the degree of the node at the end, right? So this is a very nice result. This is a fun thing. Okay, so you've got your network, boom, boom, boom. Right, and you've got some degree distribution. So now we're going to jump on an edge and we go here or here. So if we end up here, we'd have a 4, this one would have a 3, and so on. So we get a different kind of, maybe the first thing you'd think about is, okay, and we'll see this is a mistake that people make later on, is that it's the same as degree distribution, right? What's the probability that I'm going to jump on an edge, run along to the nearest, one node. What's the probability that node has k friends? Sort of, I don't know, your brain we're not very good with statistics. So, yeah. So, actually, it's this, right? So, it's related, you take the degree distribution multiplied by k, and then you have to normalize it properly. So what's happening, and it becomes clear hopefully once you see this, is that now we're sampling by edges. These nodes are bigger. Now their size is exactly the number of edges they have. Before they're all the same size, right? These nodes are all, in the sense that I've drawn them, they're all the same kind of targets. But now this one has 4 ways of getting to it. And this guy has one way, this guy has one way, there's 3, and so on. So they're amplified now. So now we're choosing by their size. But it's very nice. We don't have to say, well, let's, find all the ones that have size 4, and then we'll give them a higher weight, right? It actually just very naturally has that encoded in it, because you're randomly choosing from edges. So it's still a very nice random approach to things. You just naturally get 4 ways to get to this character here. And the way we combine them, right? So this guy and this guy, they both have 2 friends, so they go in the 2 friends bucket. This one has 3 friends, it's in the 3 friends bucket. This one is in the 4 friends bucket. These guys have 1, so this P1 is 3, if you like. I should say, so 1, 2, 3, 4, 5, 6, 7, 3 sevenths. P2 is 2 sevenths, and then P3 is 1 seventh, and did I get this right? Is 1 seventh, right? Right. So, but when we go to the Q's, we want to multiply these guys by their numbers. So this one gets multiplied by 1, this one gets multiplied by 2, 3, and 4. They amplify them. So the more friends you have, right? So it's linear. And then we have to normalize it properly. But, so is that kind of okay? So here's our normalized form. It's going to be KPK, right? That's the expansion that you get. And then we simply have to normalize. So we just sum over all degrees on the bottom. That's what this is. Which has a nice, there's actually something quite nice. So, okay, it's KPK. We're just summing over all KPK on the bottom. That's our normalization. What is this object? Yeah, it's actually sitting there. It's the average degree. So we have kind of a nice, thing. We can write it like this. Right. So this is a very important, you take your piece of K, this is a very, very important second distribution or related distribution. Right? As I said, we're going to be working with edges a lot. So we'll call it the edge degree distribution. Let's say, so we jump on an edge. What is the degree of a randomly chosen ends node? Good. Good? How do we feel about this? Emotional? Nope. Okay. Yeah, so it's probably that if it's a randomly wired up network, if we choose a random, it's somewhat true. So, so you're sitting on an edge and you want to look at what's out here. If it's been randomly wired up, right? So your friends are random. You're sitting in this thing and your friends are random, right? So let's say you were a little character that had 3 edges coming out of you, and it's all been randomly wired up. The chance that you get connected to someone that has 0 friends is 0 because they're just, right, they can't be in the game. 1 friend is whatever, 2, 3, 4, but it amplifies, right? The chance of being connected to someone who has 1 million friends is high, even if there's only 1 of them, but there are 1 million ways to connect to them. So there's a better chance of connecting to them. So this leads to an unfortunate situation, which we'll get to. There's one other that was very helpful for thinking about contagion and spreading. It's a simple modification, but it's probably that if you go to a friend or you're traveling along an edge, you find the node at the end, that it has k other edges coming out of it, right? So it has k other friends, meaning it has k plus 1 total, has you as a friend. So if you're spreading something through the network, this is kind of the right distribution to think about, right? So what's probably that as this edge is infected, it hits a node, and maybe that node becomes infected, you get k new infected edges, instead of saying k minus 1, which you could do, but. So we'll use this guy. So it's a simple modification. So the chance that this node has k friends is going to be k plus 1 times pk plus 1. Same thing, right? It's the same distribution, just shifted up by 1. The normalization is here. It's still the same normalization because one thing that happened here, when k is 0, you don't count the p0s, right? They're not in there. You can't get to them. They don't have any edges, so you'll never find them with this exploration, if you like. This one, k equals 0 is still in here, but this actually really starts, so this actually starts with, even though it's been moved up 1, it doesn't matter because you would always miss the k equals 0 case. This starts at k equals 1, right? It's 1, p1, 2, p2. So this thing on the bottom is also the average degree. A little sneaky, tiny bit of sneakiness. Right? Nothing too bad, just a tiny bit of sneakiness. If this was, k plus 2 and starting it, that would be different. We'd have to correct that. Tiny thing. Okay. Right, so this is having a friend of degree k plus 1. So, okay, so what's the expected number of friends that your friend has? Okay, if you're in a random network.
So the equation is an approximation because it starts from the factor k prime plus 1 starts from 1.
Oh, this is an approximation?
Yeah.
Yeah, no, so it's exact actually, right? So this is this oh, I could write over here. Oh, good. Yeah, so before on the bottom we had the sum of k prime equals 0 to infinity k prime p of k prime. Now this k prime equals 0, that first term doesn't matter. It's gone, right? So this is really actually the sum from k prime equals 1 to infinity k prime pk prime. We can do that, and this is the average degree, right? So if we shifted this, so now we could say k prime equals, let's say it's I've got primes. I guess I should keep them. Let's say k prime equals j prime plus 1. Eek. Yeah. So these two terms in here become j prime plus 1. The first part, p of j prime plus 1. And k prime equals 1 to infinity, so j prime will start at 0. That's when k prime equals 0. So this is j prime equals 0 to infinity. So both of these expressions are equal to the average degree. And it's because that first term never counts. When it's 0, when k is 0, you can just get rid of it. So is that got a twitchy eye. I'm gonna sneak back in. Okay, so object permanence. It's good, right? So right? That's a little, this is, tiny bit of sneakiness here. Yeah, I don't think, we wouldn't want to do plus 2. These are just sort of, this is a reasonable thing, right? This is just sort of as far as we want to go with this. There's these two distributions that are related to each other, and sometimes it's better to use one or the other. Usually we want to use this R1 because we're worried about how things spread. Okay. Really good. This is great. It's not great. I tell you what's good. Oh, it's a thumbs up. It's bad when the audience does this. It's really rough. The freshmen, I'm sure you call them freshers. It's non-gender specific. They suffer in the same way. Okay, so let's see. So, all right, so we're on a link, and we're going to look. So, because it's randomly wired up, as I said, your friends are random in this network. Okay, so let's have a look at a random friend. Here's your edge. You go out and look at them. What is their number? What's their average number of friends like? So, so this is okay. What are we going to do? So this is this is RK again. Has k other friends. Did I do this? Oh, I guess I've. This is. Okay, let me do this. All right, good. Okay, it's a bit torturous, but anyway. So we're going to find the average. We'll call it sub R. This is the number of other friends, right? This is the average number of other friends. So it's the standard kind of thing, KRK, right? We're summing over this thing. This is the probability that they have k other friends. We want the expected number of other friends. You need a Vine video, it's great. I do like seeing jelly being squirted out of a bottle. Jam, it's jam. Okay, so we're going to put this guy in. We just argued that it's k plus 1 p of k plus 1 divided by the average degree, right? That's RK, right? We said it's this thing. Okay, so we've got k plus 1. All right, now we have to, this is just a constant, so we're going to extrude that. No, we're going to pull it out the front. Similar kind of business as before. We can say k equals 0 is going to squash all this, right? So we could start, this is a little sneaky, but we'll do this again. We'll start from 1 and we'll go up to infinity. That's just, it helps us in the next step. I mean, you can always treat that at some point, but it's just, a little bit of tidying, right? We're sort of, this is a kind of a excess statement here, this k equals 0. So we get rid of that. So we'll say k equals 1. So all of this is the same still. This is a little sneaky, okay? So this guy is still here. This is just a constant at the front. But what we're excited about here is this k plus 1 and this k plus 1 here. So that's good. Those things are kind of matching up. You want to try and match up, right? These quantities. But this is a bad guy. So we're going to make it, I think you can see, we're going to make it k, we'll write that as k plus 1 minus 1. That's all that's happened there. Right, we really want to see k plus 1s everywhere. You do this in a lot of different ways in a lot of different kind of mathematical settings. So this is k plus 1. We're desperate to have k plus 1s everywhere. So we do this. That's this guy, k plus 1. And so now this is k plus 1 all squared minus k plus 1. Goody? Delicious. I mean, you can do this in all sorts of ways, but this is a particularly torturous approach that I've chosen for you. So we've matched up the indices. And now you can say, okay, k plus 1 is great. Let's call it j. We're going to call it a blob, blob, and glob. So now it's going to be j squared minus j pj. And if k is going from 1 to infinity and j is equal to k plus 1, then j goes from 0 to infinity. Yeah? You always have to think. That hurts a little bit. That always hurts a little bit, I think. Yeah? What's that? PJs. Oh, good. Yeah. Yeah, that would have been much better. Yeah. PJ the whole time. Yeah, K has been sort of stuck with, yeah, all right, okay. PB and J. Okay, so this is good. So now we have, sitting here very nicely, we have, so 1 over this average here. The first bit is the second moment, right? This is talking about, right, this edge degree distribution. Now we've got it all the way back to our underlying degree distribution. That's what this little particular battle was about. We don't know what the underlying degree distribution is, but we know how these edge degree distributions relate to it very simply, so we have to do a little messing around. So now it's the second moment of this degree distribution minus the first moment. So we can look at that for a little bit and think about it. Seems what? Seems legit. Okay. So this is going to be the number of other friends on average, right? So you go to your friend and you say, how many other friends do you have? I mean, I'm concerned about our relationship. This explains why this will explain why on Facebook, not really, but it kind of, a little bit, why on Facebook everyone seems to have more friends. Because on average it's true. Your friends have more friends than you, which is really disappointing. So this is, of course, let's go. Okay, so we have this guy. So this doesn't matter what the degree distribution is, right? This is just for P sub k. It could be anything. But let's just go back to these ones that are, dominate the story if we're choosing from mathematicians' heads, right? So the Poisson distributions. We had this quirky result that the second moment is the first moment squared plus the first moment. So we're going to stick that into there, and you can see some things are going to happen, right? Okay, so this goes boom. It's the second moment, gets replaced with what we find explicitly just for Poisson degree distributions, not true in general. These guys are going to cancel, and then we have the mean squared over the mean. Cancel, cancel. Just the mean. It's very strange. So on average, you go to one node, and they have, let's say they have on average, 7 friends, 7.2 friends. They have 7.2 friends on average, right? Then if you jump on an edge, this is only in these particular graphs, networks, these Poisson degree distribution ones. You run along the edge, you look at that person, and then they'll have on average 7.2 other friends. So on average, they have 8.2, right? They have one more than the, so running along an edge, you always find on average one more than than if you just jump on a node and look at its degree. So that's a little funny, right? I mean, one thing you know about your friends is they have at least one friend. You could think of it like that, right? They have at least one friend. And you'll never find any of the no friends situations, right? So if there's characters with no friends, you don't find them by running along edges. But you occasionally, you'll sample them, with the node-based sampling. So let's say edge sampling and node sampling. Let's try that. So this is just for Poisson. Just for Poisson. Okay, and it's going to give rise to some bad mistakes. Okay. All right, so this is our story, right? So on average, they have the mean +1 friends in total. Cool? That's a nice little result. See, it's all very good. Yeah. It's math, you can check. So why does this matter? So you have a node, right? Let's say we're at some node. This is not exactly contagion, but it's kind of getting to that idea. So we're at a node, has some friends. So that's the first layer. And then outside of that, these guys have friends, right? Some of them are friends with each other and so on. So there's all sorts of things like this. And so on, right? But these are your friends of friends. You don't know these people, but they're friends of friends. So you might know about them. They keep talking about this. Stop talking about it, right? This is, they're always going about their friends. And of course, natural social mechanisms. This is a triadic closure thing, right? So you'll get introduced to these people, potentially. Yeah, so that's how it changes. But there are friends of friends of friends. And this is kind of the edge of your social universe. There are lots of studies that suggest this is about right. That like correlations of things in networks, in real social networks kind of end about here. Your friends are similar to you in certain ways. So your friends of friends. These guys a little bit too out here. But then these people are basically, this is randomness, right? This is the void. This is like, who knows who these people are. But, so, all right, nice thing, and we talked about it recently, right, was the NSA saying that they're only allowed to go from, so 2 steps. So now this is apparently their limit. So if they find someone of interest, they can go out to here. But before they were going out to here, which is essentially the edge of the social universe for any human. Okay. And of course, you just need, what's a link? Is it just because they accidentally sent some mail to someone? Does that become a connection? They never talk about the strength of ties, right? Because if you have really weak links in there, you accidentally called Al-Qaeda once. You were trying to order the pizza and you called, then you're in the, you've got it in the list and you're in the matrix and you're your friends. Or the White House, you're like, oh, this person knows Obama. No, not true. Okay, so friends of friends. So how many are out here, right? So you have this average degree K out here, and then what's out here? On average, in these, this is just again these Poisson guys. All right, well, it's your average degree times the average number of other friends that each one of these guys have. This is a little, you have to think, well, but it's random, so there are no correlations. It's good, right? So the number of other friends this one has nothing to do with this one. It's random. Not a very social thing. This is a real network, so there's these cross connections. In the random ones, it's pure branching. All right, so let's put those things together. We have average degree, and then this quantity we just calculated. So these pieces are going to cancel. So it's just the second moment minus the first moment. Okay, this is now we're stepping back out to general random networks. Okay, so we could replace this with the Poisson one. But this is a general random network story. So here's the sort of big piece about this is that it depends on the second moment, right? So the number of friends that are out in this first layer. So this is your mean. So in fact, let me write it in. So it's K second moment minus the first moment. So the variance it's not the variance, but it's the second moment. So the variance is connected into here. So if you have a distribution with a really big variance, then that starts to come into play very quickly, right, in terms of how the network is structured. So say it has an extremely large variance, then you have your friends. Maybe on average people have 5 friends. But if the variance is enormous, then it just goes, it blows up immediately. All right. So it's not just the first moment. You might think, okay, well, it's in here. All right, so here's the naive thing you might think. And I've written this as K sub 2. This is terrible notation, but that means the number of friends 2 steps away. This would be the simplest thing to think. You might think it's the average degree multiplied by the average degree minus 1, because, right, this is if you're not thinking about this edge degree thing, right? So you travel out to someone, they should just have the same average degree as everyone else, right? So you subtract 1 because you're their friend already. So you might think this would be the simple calculation. But it's actually, if you look at this, it's not this. This is a mean here and a mean minus 1. It's actually the mean of that product, which is kind of nice, right? So there's that. We got to it in a different way, but this is just a little observation at the end of it to show they're connected. So as I said, so if the underlying degree distribution has a big second moment, has a large variance, which happens a lot with scale-free type networks, then this can be huge. Power laws. And so, unfortunately, your friends really are different from you, right? And so there are some old papers on this. I don't know why my little mouse disappears. Come back, mouse. There's this one by Feld, right? So, why your friends have more friends than you do? It's the American Journal of Sociology, which is the top journal for one of the top journals. It's 1991, so of course this is before physicists came along and rediscovered many things and other things. And so the next one is, so it's ego-centered networks and the ripple effect. So this is Newman, but he actually called it, or why your friends are weird. But I mean, the straight-out statement is that they have more friends than you, which is really bad. And you could imagine all sorts of other reasons for people being connected, and also, right, we're connecting here randomly. But if there are characteristics for why people connect, you could start to see strangeness in that second layer again. Like everyone in the second layer might like yoga or something. It's just you're like, what is going on? It's just your friends are strange. Okay. So it's in statistics you might call it class size paradox, right? You're selecting now because involved here is this selection of nodes based on their numbers of friends, right? They're just all individual people, but you're selecting them based on their size. All right. Just a little extra thing to think about here. So you have your number of friends. This is again for general random networks with a particular degree distribution. Your friend's average number is, that's true, right? Okay. Yeah. Okay, so this is how many are out here in total. Right? Yep. So each one of these friends has you as a friend. Am I getting this right? What am I saying? You have to add the other one. Yeah, it's plus K. This is there's yourself, right? So that matters, right? That's what I'm confused about here. There are, right. We want to go back to our other one, which was 1 over K. This is what I want. Yeah, K R. Right, is this one. Okay, this is the average number of other friends that a friend has. So therefore, if we did K, we could actually figure it out as well. But KQ, which is the total number of friends, in here there's really, right, let's write one more step. This is the second moment divided by the first moment, and then this is really minus 1. So KQ includes you, so you just add 1 to it, and that's going to get rid of that guy. Okay, good. Is okay? A little bit of lying? All right. Okay. No, that's okay. Yeah, this is one of your friends' average number of friends. So we want to compare these two things and see in general if they're how they compare to each other. All right. So, okay, this is your average. This is you look at one of your friends. This is the average number of friends they have, total, including you. So we're going to play around with this a little bit. We're going to do some because we want to force things. So, okay, so we're going to pull out this average degree here and then put a square on the bottom. And the thing is that this is the variance. This is close. This is right. The variance is this guy minus the mean squared. So we can replace the second moment with the variance plus the mean squared. Right. Definition of the variance. So it's the square of the standard deviation. So now we have not a bad thing. So this is really, there's a 1 here for this. That's this guy. And then we have the standard deviation divided by the mean squared. Right. The reason for doing this little bit of maneuvering is that we want to compare it to this is our friends, average number of friends. We want to compare it to ours. So we pull out an average degree, we'll just put it there, and then we want to see what this guy's like. That's what we're, is this always greater than 1? Or, is it possible it could be less than 1? Okay. Okay, so we mess around with a little bit and we see, okay, your average, your friend's average number of friends is your average multiplied by this piece, and you can see this is, it's 1 plus a thing that's always positive, except when there's 0, the standard deviation is 0. All right, so it's always greater than or equal to your number of friends, which is very disappointing. So the only time you get it is when the variance is 0, when everyone is the same. No one is special, okay? Pox reference, okay, very obscure. Community, okay. So when everyone is the same. If everyone is the same, the standard deviation is 0, everyone has 7 friends, then this would be, right, these guys are the same. Yeah, no, okay, yeah. So this is a bit confusing. We go through this. The Poisson piece, which we'll come back to because we can't help ourselves, is only really this page. But as soon as we get to here, this is all general again. All general. Yeah, so this is a general result. Yeah, so this is a general statement. So with Poisson, we can say some more things about this, right? So we know that this is actually the mean squared plus the mean. Here. So in fact, it would be, in fact, I guess we could put it here. Means, okay, let's get the Poisson result. Good. All right, hopefully I don't have it on the next page, now I'm confused. K squared for Poisson is equal to the mean squared plus the mean. So if we're dividing that by the mean, it's the mean plus 1, which is what we said before, right? Yeah. That's good. Yeah? So in Poisson, they always have 1 more than you. But in general, it's this ratio, 1 plus this is the ratio that they have over you, right? So only in the equal apportioning of friends situation, in a world where where the government decrees how many friends you can have, are your friends the same as you? Yeah. All right. Yeah, and so you can get a feel. There's a feel for it. I mean, we have an exact quantitative thing now, right? And again, this is for random networks with arbitrary degree distributions. But the underlying feel is that you're more likely to connect to someone who has lots of friends. Right? They're easier to find. Yeah. Okay. And it can go crazy if you have a really high variance because it's easier to connect to these huge. They're very easy to find. Someone has 10 million friends, which is not true, right? The world can't do that. But something like Twitter, where you can follow people, and if you count that as a relationship, then it goes off the charts, right? I mean, there is, what is it? Who's in front? Lady Gaga? It's an indictment on humanity.
Right, yeah.
Who is it?
It's between her and Bieber, right?
Yeah, Bieber. That's interesting. Bieber may have taken a hit. Or maybe he's got more. Maybe he's discovering new pools of... Okay, thank you. That's true. There's accidentally a number of things. I'm going to need a mango. Who is it?
Katy Perry.
Oh, wow. Wow. Lady Baba? No, Lady Baba. Obama is 2? He's 3. Lady Gaga. Twitter. Number of followers on Twitter. just because this is that's a ridiculous example of where you can get massively skewed distributions for whatever it is, but for this one, it's follower counts. Some of whom are humans, right? But a lot of butt action out there. Okay. So, all right. So this matters. It's not just for fun and thinking that you're not as popular as you thought, but it really helps with this is the basic glue story for how these things are connected together. And so it turns out something like finding what's the largest component size. What's the size of it? Is there a giant component, for example? A property of random networks is that, and I'll say this, I suppose, in other ways, is that you don't have two giant components, right? Or three. There's always just one. It's because the chance of the things being distinct is zero, basically, right? You can't have random wiring and not have two giant components somehow be connected. But a really basic question is, is there a giant component? And this may be part of the network itself, or then the network with a process run on it, right? So you imagine you take the network and you spread something on it, and then you could say, the ones that got sick, for example, it's contagion, the ones that got sick, that leaves you with some of the network. How big is that? Is that thing giant? What proportion of the network of the world gets infected? All right, so you may use other words. You may have seen other words for this. So when we say component, so we made it has to be a connected subnetwork, right, of nodes, so that you can find a path from every node in that subnetwork to every other node. It's one of these things that takes it's a lot of words here, but it is what you should kind of be able to intuit. And then a giant component is one that if you look at the thing macroscopically, right, here's your network, you can see a big clump, right? Giant component, it's macroscopic. So it takes up a non-zero fraction of the network. So a non-zero fraction of the network is in a giant component. People will say cluster as well. Yeah? Clustering, I know, but we won't say it here because we say clustering for something else. Yeah, but you might say that. Yeah. Best to avoid those people. Yeah. Okay. All right, so here's a little example of a largest component story. So we'll get to some fun ways of figuring this out. All right, so this is Poisson, just a Poisson example. S1 is the fractional size of the largest component. So you take your network and you find all the components. All right, so a component can, of course, include one isolated node. That's a component. And you order them, right? There might be 30 components. 27 are nodes without any friends. And one has 7 friends in it, another one has 2, and there's one with 80 billion friends in it. All right? And we'll call them S1, S2, and that's the fractional size. So S1 is the fractional size of the largest one. So for Poisson, guys, we're tuning Poisson, and we saw this in the first lecture. We saw some of these pictures, but this is the fractional size of the largest component, right? So you don't see anything until we get to 1. So there's something crucial about 1, and then we have this nice phase transition. It's a spectacular phase transition. And it's getting closer and closer to 1, and this is actually only by average degree of 4. Almost all of them are in the team here. And these are examples at particular values, right? So that's at 1. This is pretty bad. It's at a half or something like that, and the largest component is 4. So these are taken from before, it's 500 nodes. That's almost all broken up. Cool? Not cool? Kind of nice. So, one of the big games that's been going along for spreading, thinking about good things, bad things spreading, is whether you're on this side or of this phase transition. Badness is over here, right? So if somehow your system changes, the thing becomes more infectious, people connect with each other more, then boom, right? That's bad. It will take off. But here, it's the final,
I guess, when I see this, it makes sense talking about contagion, but I thought I've heard you or even Maggie say before that with contagion, it's not necessarily the most well-connected person.
Yeah, so we talked about that in Pox, right? Yeah, we talked about it in Pox. So that's an entirely different thing. So it depends on the mechanism
Okay.
that's running. So simple kinds of contagion ones, which is just, if someone is sick, you have some probability of transferring, that's it. It doesn't matter how many friends they have or how many friends I have. You just, if you have 10,000 friends or 3 friends, you somehow interact with all of them in the same time step. Those things spread, pretty well. The thing has to be connected enough. They'll spread even better. The more hubs you have, the worse they are. But there are other things, and some of these examples of social contagion fit into that second category, right? Which is, if you have say on Twitter, for example, you follow tons of people. The input from them is, you have to threshold it, right? So you see one mention of something out of 10,000, it doesn't tell you it's a big thing, but like this movie of the goat thing got spread everywhere, right? So whether you spread it or not is up to you, but you get that's a different signal. Yeah, so look, all that stuff is old stuff that they quantified things that we wondered about, other people wondered about. It's very nicely done. But it's, so there are different reasons for spreading things, for adopting, for behaving, than the simple kind of spreading models that you might think about. And then, the structure of the network matters a lot. Yeah, so it's always the structure of the network, the particular mechanism on top. So it's not this simple story where you'd think more connected people will make the thing spread more. That's a big result. We'll come to some of that here. But this is just about Poisson. These are just these random networks, pull them out of a box, looking at them with different average degrees. They have this thing. But here's the big story, right? For these things, it's really the big story, that there's a giant component. And right at this point, there's this kind of tendrily thin thing, which isn't quite, it isn't macroscopic, you can't see it, but it's just, it's just like ice forming, right? It's right at, these are phase transitions, right at that edge of in between. Okay. All right, so let's get the condition for that, right? We can do that, and we'll do this in more elaborate ways, more well-defined ways, I think. So this is good thinking, though. So we're not talking about spreading yet. We'll get to that. And we did cover it, yes, but we'll get in. This is going to be much more quantitative. So there's a giant component in the network, in general, for these random networks. If you just jump on an edge and you go towards one of the nodes, that on average you find more than one other nodes out there, right? So that right? That's the simple criterion. Now, there's going to be, you jump on an edge and there's only 2 friends. That's the end of it, right? It's just a little dyad, right? You might find that, fine. Or you might jump on this edge and go this way and it just ends at a tendril. But the point is that on average, if it's greater than 1, there will be a branching process occurring, right? So you find 3 at the end. So you go and then there's 3 friends. That one branches out. Maybe this one only has 1 friend. So it dies, and this one has, but on average it's growing. So it's an exponential growth story. You will have it will take off, right? So you keep jumping on this network, you jump on an edge, and if the average, this K-sub-r, right, the average number of other friends a node has, if that's greater than 1, the whole thing, then on average you see an exponentiation, right? Grows. So it's the same. So right, exponential growth. So that's the criterion for random networks, arbitrary degree distributions. We can say this, and we can start to say this in more generally, but this is where we are. So and we'll frame this in a clearer way. I'm going to have a whole body of stuff later on, which gives you a more. We've just derived this, right? But we'll give it a much more physical kind of explanation. So it's this. This is a well-known result now. Simply that this is greater than 1, right? This is the thing we found before. So it's the second moment minus the first moment divided by the first moment. As long as that's greater than 1, there is a giant component. So this is a nice little test. You take your degree distribution, measure these 2 things, second moment, first moment, calculate this little piece. If it's greater than 1, there will be a giant component. So that's a nice achievement, right? And I'll give you a more intuitive way to even get to that later on. But so second moment is huge, right? So if the well, literally, but I mean it's important. If it's large, then yeah, your chances of this is greater than 1 become, right? Depends on the mean, but yeah. So if it's really, so power law things. So this is a very famous result in complex networks, is that for these power law size distributions where this thing is infinite, then essentially, right, this is what the calculation was, this thing is kind of infinite, then, or very, very large, then spreading occurs on those networks all the time. Or they have a giant component, you know.
Did you say that this kind of generalizes to other than random networks, or is this only
The same idea holds, actually. Yeah, right, it really does, right? Because it's all about whether, as you move through the network, you know, as you've moved n steps away from you, is the number of nodes that you've explored or reached growing exponentially, or growing in some way. So if it's not random, then it's more complicated, and you may have some other thing. But is it somehow, is there an expansion? Is there a local expansion? Random networks have these very nice properties, right? So they have that they're locally branching, so we can do all sorts of computations for them. But the same kind of feel is there, and what you would have to do, say you've got the power grid, right? And I mean, that's a complicated thing to simulate and whatever, but you could think, well, is there an exponentiation as I move away from one point? Or you've got some social network, right? You might find that, that doesn't really happen. Like it's kind of a distributed thing, so you don't really, sort of people all live in a line, like they're in Chile, and they don't really, it doesn't really grow exponentially. Yeah, but many networks, it's very much true. So you can mess around with this and get nice little mathematical statements, right? So we could do this, we'll put this over here, and then put this guy over here, so it's 2 times the mean. So now we have the second moment is greater than 2 times the mean. It's kind of strange, right? Like that's a little harder to understand what that means, but but this is something that arrives as a result of mathematical examinations. Anyway, so good. You know what we'll do? We'll finish this set of slides and then we'll have a break. And then we'll go into generating function action. All right. Okay, so this is a step back to the Poisson ones, just to kind of see how they behave. So this is our condition for the giant component is that this thing has to be greater than 1. And so let's put this stuff in. So we have that the second moment is the square of the first plus the first again. Okay, so we're going to stick that in here. Boom. And again, these two things disappear. We have these things cancel, and we get the average degree. So this is, this turns out to be a very simple thing. So for Poisson, it's just sitting right there. Okay, I have a Poisson degree distribution. It's a random network, and it has an average degree of 1.1. Well, that has a giant component. Because this criterion was whether or not this is greater than 1. And that's exactly this result, this picture. That's why this picture looks like this. 1 is the bit. So we've analytically determined why that is true. Okay, which is a bit funny. That means on an average you just have one friend. It's not your average person is a dead end, right? They've got one friend. They have no other friends. They're like, that's a cool video, and they can't. Did you see the video? It doesn't. They're hopeless, right? They're no good. So what you really need, so at that point you can start to think about the details. They're enough with 3 friends, for example. Like 3s become kind of they're an important character. You need those because they're going to help exponentially. If you've got 2 friends, you're just kind of maintaining the thing. If you really like spreading stuff, that's good. But the 3s and the 4s and the 5, they're the ones who start to spread out. And so far, we're not really talking about spreading. We're really talking about giant components. So it's just structural, right? So you can imagine a spreading. You can think of a spreading for free. Every time someone gets something, they go boom. They just send it on. Goat video. Yeah. Okay. So, but it is. It's low down. So there are people in these networks. There are nodes in these networks. there's some proportion, you can think about what it is, you can look at your Poisson. There's a proportion that have 0 friends, right? There's a whole bunch of zeros out there. There's some that have 1s and they're all dead ends. There are some that have 2, 3, 4, 5. But there's just enough right at this threshold where the average friend is useless in terms of spreading or connecting, that there are enough 3s and 4s and 5s to glue things together, start to glue it together such that, I mean, it's right at the edge. You're starting to glue them together. You're getting a tendrily kind of structure. And you increase the average degree just a little bit more and you can see it from space. You can see a clump. Okay, that is groovy. Okay, so that was this calculation. So yeah, when your average degree is less than 1, you have finite components. The largest one is doesn't scale with n, algebraically. All right, so it's a phase transition story. Beautiful things. It's a continuous phase transition, right? Yeah, it's not a... I mean, these are kind of the terms we've ended up with. It's discontinuous and continuous. There's not a jump. There are examples of discontinuous ones, right? So it's a critical point. So we talk about this being the critical point of the system if we use that kind of physics language. All right, so let's just do a little more. So this is a random network story. Let's imagine we have a random network with a power law size distribution. Let's say gamma is between 2 and 3, right? So it's decaying as k to the minus gamma. There are no nodes of degree 1. So, right, there's a normalization constant. You guys have figured all those things out before. It's a zeta function, actually, right? So the second moment is the crucial piece here. So we're just going to compute it, k squared. Here's our distribution, k to the minus gamma. We approximate this sum with an integral, because we're bad people. But you could, what's that? It is a zeta function. We don't have to do this. But anyway, so it's a x to the 2 minus gamma. We're just being lazy. Yeah, fine. And integrate this thing. So it's x to the 3 minus gamma. There's some constants. We have proportional signs. And we said gamma is between 2 and 3. Kaboosh. Right. So this explodes into flames. And so for these guys, which is much larger than the average degree, so we always have a giant component for these kinds of networks. So I just showed you some examples for ones with 1,000 nodes, it's not enough. We always have them. So k to the minus 3 is the cutoff, right? So if gamma is greater than 3, then we have to actually really compute this, this quantity and see if it really is greater than 1 or not, but probably. Okay, there's a tiny little question to finish with, which is what about if it's everyone has the same number of friends? That's what this is, right? So k naught is some thing. You could compute this, right? No? So what's this guy? It's kind of a nice question. Yeah? Let's do it. All right, we'll go a little bit and then we'll have a break, okay? We're just going to get to these end of these slides. Keep going. All right, can you tell me what was this? What was this thing? Is it this? What is it? Yep.
K squared minus
Okay.
and it's zero everywhere, but they're not the same thing.
Yeah, so it's a spike, right? So delta k0 equals 1 if k equals whatever this one is, 0 otherwise. The Kronecker delta function, whose continuous friend is the Dirac delta function. Which is a truly spectacular object. Yeah. Yeah, well, so what's the average degree for this distribution? Mm-hmm. Well, okay, yeah. Let's write these guys down. What's the average degree? It is. It's K sub, it's K naught, right? That's all. Just, that's what it is. Everyone has the same. And the mean, the second moment, right? Because you're going to say 1 times, yep, okay. Is that okay?
Wait, why squared? Oh.
Mhm.
Yeah, yeah, okay. I agree.
Is it okay?
Yeah.
Okay. All right. So this guy becomes 1 over K0, just for this example. K0 squared minus K0. So we can cancel some of these guys. Right? So this is going to go away, it's going to go away. So it's K0 minus 1.
Yeah.
So, which is, so this guy is equal to 1 at K0 equals 1, sorry, 2. And it's greater than 1, of course, if K0 is greater than 2. So it's right at the threshold, right? So when everyone has 2 friends and you randomly wire this thing up, you're going to get some really long, linear things, and it's not a very good network. You just get these long, long chains. But when it's 3, you get a fantastic, lots of connections, right? So, and it's 2, which is a nice, healthy number. Okay, so that should make sense intuitively. We're definitely getting there. Okay. Sorry. So you want to know how big this thing is, right? So now we've just got that point. We said, okay, there's a phase transition at 1. Analytically, we've done that. We'll give you a rest in a little bit. Okay. Oh, you humans can have it. It's okay. So, how big is this largest component? So that's a really, right? I mean, we say, oh, it's it's going to spread, and then someone says, well, how big will it be? Is it going to get 10% of the population, 90%? And we don't know. We just know there's a phase transition. So that's no good, right? So we have to compute the final size, which turns out to be very hard, even in some random networks for certain spreading processes. And we'll come to that. It's a beautiful result. I've shown you a little bit of it before, but we'll really get into it analytically. Okay, so let's just do pure random networks. And we'll do something sneaky, right? This is why we'll need to go to other methods. We'll do a sneaky thing, and we'll get it all wrong. So back of the envelope. So this is going to seem okay, hopefully. So delta is going to be probably the randomly chosen node does not belong to the largest component, right? You've got your network, and then delta is we're going to choose a node. Delta is that probably that's not in the. So it turns out a lot of the analysis you do, you avoid the giant component because it's got cycles in it and it's kind of nasty. So you actually calculate everything about all the little ones that seem irrelevant. And then you say, okay, 10% are not in the giant component, therefore the giant component is 90%. So it's very sneaky, typical kind of math badness where you're like, monks died to get there. But right? You're looking at this thing and everyone else says, no, you need to look at the, the negative space, basically. Right? It's good. It's a very clever thing to have done. Okay, so that's exactly the thing. So the simple connection will be, it's delta, this little delta has to be 1 minus the fraction that the giant component takes up, right? Or the giant component is 1 minus that fraction. Okay. So this is true, right? So if a node is not part of the giant component, then none of its neighbors are. Okay, that's good. So we can do this, right? So we could say this statement should be true, right? So that there's a little recursion relation. So we have lots of recursion relations for these things because random networks are full of this. So we could say, all right, well, let's randomly choose a node, okay? And we'll look at its friends. So we're going to say something about this node based on its friends. So this has to be tautologically kind of true, basically, right? So that if you have k friends, then none of and you're not in the giant component, then none of your friends can be in there. So it's delta times delta times delta times delta. And then we sum over all of them, and that has to equal your chance of not being in the. So people use it. These are in textbooks and things. It's okay. Yeah, right? Yeah, maybe. So something bad has just happened here. All right. We're going to put in a Poisson distribution. You can think about what that is. All right. So We'll actually stick it right in. Okay, this is a Poisson degree distribution here. Good. This thing can come out. We have a delta k here. And the delta to the k can become friends with this average degree sitting here to the k. So this is a blob to the k. Yeah, these guys are here. E to the minus k, that can come right out. And the k factorial is on the bottom. So this looks like an exponential again. Good. So in fact, it's this. It's e to the minus the average degree, and then e to whatever this blob is here, right? So it's average degree times delta. So you can connect those two, pull out the minus the average degree here. It's nice, right? Good. This is good hygiene. You always write it like this. This quantity is positive. 1 minus delta has to be positive. So we're going to put it like that, and we'll put a negative sign there. So we have delta is equal to this bit. So this is I mean, it's nasty, but it's solvable, right? It's a nasty little equation. We're going to flip things around. We had delta is 1 minus S1, so we can now put, so this is the size of the fraction of nodes that are in the giant component. So that's just going to be, okay, so delta is 1 minus S1. So we'll put that here, and then we'll flip everything around. So the S1 will come over to this side, and the 1, if you like, and the 1 can go to the other side. So they're the same sign. And then we get a negative in front of this guy. And because it was 1 minus delta, it's just S1. Okay, so that should be doable. We will have to do it, we'll have to solve it computationally. It's okay. And that's correct, actually, right? So we can do a few things. We can actually find some limits. In fact, you can invert this. And so you can actually write, as we can tune the size of the giant component from 0 to 1. And you can actually invert it, 0 to 1, and so we can write the inverse function, right? Okay, so we can actually put that plot. In fact, that thing that I showed you is in fact this function, right? That plot, right? The phase transition. This is in fact the right shape. And so it goes below, the function itself goes whoop to 1, and in principle, keeps going, right? Analytically, you found something like this, all right? So it does the right sort of thing. So the average degree goes to 0. The size goes to 0. That seems right. So as this is going to 0, this is going to 0, then this is decaying. Let's see. So we'll get this right. Right. Yep. So that's okay. This is not a big deal. As the average degree goes to infinity, then we get the other thing, right? So average degree goes to infinity, this becomes 0, so we have the fractional size goes to 1. This is good. So we have the critical point when it's 1, when this guy is 1, then it works out, right? So if this is 1, e to the minus s1, so 0 equals 1 minus 0, that's fine, that's a solution. It's okay. It's always a solution, it's true, but okay, yeah. Okay, so there's some nice things about this. So it's this is a transcritical bifurcation story here. Yeah, thank you. Which, there's a solution, there is always S1 equals 0 as a solution. There's this other one here. Fine, good, okay. You can play around with that. All right, so this is what we had. Okay, so here's the end of this. So we did a naughty thing, right? So it only works for Edish-Renyi networks. So it doesn't work for general random networks with arbitrary degree distributions. So why is that? So here's the problem. We assume that the neighbors have the same probability delta, but we've already seen that your friends are different to you in various ways, right? So this was a bad thing to do. And it works because of this, right? That there's this very special property of Poisson degree distribution networks is that you go to a random friend, then they have exactly the mean of the distribution of the Poisson distribution as the number of other friends. We'll get to this later, but you actually need a separate thing. You actually need to do you need to think about another delta for what's the chance that your friends are not in the game. You have to think about a different thing. There's U because we're choosing by edge there and we're choosing by node, so you're not allowed to do it. Okay. All right, so we're going to get into generating functionology. And I'll also give you some other ways of deriving things that are simple, straightforward, probabilistic. But there's a big fail that just happened there. That is, we're able to get to the phase transition. That was good. We were right. But finding the size, obviously a huge thing. And there's lots of other things you can do. But that's, yeah. So it turns out we're going to have to take a little detour and get some, load some other things in. All right, so let's have a break. Yeah, yeah.
So was it an accurate definition for giant component, or did you say that?
What's it? What is the definition?
Giant component.
Yeah, so giant component. So a component, any component, right, is something that is, so it's a subpart of the network, subnetwork, where there's a way of getting in this subnetwork from any node to any other node in that subnetwork, right? So it's connected. It's just connected, yeah? And it's a giant component if it takes up a non-zero fraction of the whole network. So we're always, with these random network models, you think about n going to infinity. Or we think about bigger and bigger networks. It's a giant component if it's macroscopic, in the sense that you could see it from space. You stand back from the network and you can see a ball there somewhere. The big point, I suppose, is that there is no giant component up to some point, typically, and then so you're searching through. There's all network space, right? And with the random network story, with the pure random networks, what we're doing is we're tuning the average degree. That's our right. This is vast space, and you could explore it and travel through it in all sorts of ways. The average degree is a very nice kind of road to travel along, right, through this vast hyperdimensional thing. So you travel through it, you're looking, and as you move along, you say, okay, now I'm in the world where they're random networks, and they have this average degree. And you have a zillion of those guys. And we think about them with infinite number of nodes, or limiting towards that. And then we move along, and now they've got a higher average degree, and now they've got a higher average degree. And suddenly, if you're looking at these, you'll see, oh, now they have you can actually see them. Instead of being all these little points and little tiny little pairs and triples and so on, you see it starts to pop. So that's the idea of a giant component. And for spreading, it becomes, there's this kind of the same idea. Will this thing spread to a large part of the population? First of all, it has to be connected enough. So it has to have an underlying giant component, which is true of social phenomena and ecosystem. I mean, they're in power grids now, right? So power grids didn't used to be like this, right? They used to be separate little stations, and we got them to work, and then we started to put them together, and then we get to continent scale stuff. Then funny things can happen. Yeah. Let's have 15 minutes, and then we'll have a shorter piece to make you happier. Yeah. We ate too much. But, I made you eat too much. All right, people.